Hello, and welcome to this film, which is basically all about burning things and trying to find out their formulas. In the previous film, we learned about how to calculate an empirical formula and turn it into a molecular formula. Well, here we're going to be doing very simple problems, very simple, very similar problems, but the information that we're being given at the start of the problems is just slightly different. Slightly more disguised, I suppose you could say, than it was in the past. Okay, so we're going to have a look at how we can burn a substance and find out by analysing the products about how many atoms there were in that substance. And having done that, we'll see how we can turn an empirical formula into a molecular formula again, but this time with slightly more complex information given to us. Okay, well, let's start off by looking at how we might carry out one of these experiments that would give us the data. Okay, it's called combustion analysis. So in other words, we're burning something and we're analysing the products. Okay, so our sample here is the thing that we want to burn. We put it in a furnace because we want to heat it up. We're burning it, so we're providing lots of oxygen. And what will happen here is that any hydrogen atoms in here will combine with oxygen and make water. And if I pump the products through this system and I put something in this next chamber that absorbs water, then this substance will gain mass because of the water that it's absorbed. If I know what mass it's gained, I can figure out how many moles of water there were. Similarly, if the products will go even further through this system and bump into something that absorbs carbon dioxide, then any carbon that reacted with oxygen in here will have turned into carbon dioxide and will cause the mass of this to increase, and so I can figure out how many moles of carbon dioxide there were. Now, why would I want to know the number of moles of water and carbon dioxide if I'm trying to find the number of moles of carbon and hydrogen? Well, carbon dioxide has one carbon in it. So if I know the number of moles of carbon dioxide, I know the number of moles of carbon that were in the sample. If I know the number of moles of water, water's got two hydrogens in it. So if I take the number of moles of water and double it, then I know how many moles of hydrogen there were in my sample. Okay, so now that we know a little bit about how the experiment works and why we're doing it, let's have a look at an example problem. Okay, analysis has shown that benzene is made of only carbon and hydrogen. So I'm going to be calculating an empirical and molecular formula, so they're the two elements that are going to appear in the formula. Okay, a sample of benzene was burned in excess oxygen to make sure that all the hydrogen turned into water, all the carbon turned into carbon dioxide. Okay, and we formed 32.4 grams of carbon dioxide and 6.63 grams of water. Then later on, a 10-gram sample of benzene was found to contain 0.128 moles, and we have to find the two formulas. Okay. Now remember, every time I'm trying to find an empirical formula, I'm trying to find a ratio of atoms. So before that, I have to find the number of moles of them. And usually I'm given a mass or a percentage. And the two elements that I'd have in my table here would be carbon and hydrogen, okay, because they're the ones in my formula. The trouble is here that I'm not told about the mass of carbon or of hydrogen. So what I'm going to have to do is find the number of moles of carbon dioxide. Remember that the number of moles is mass over molar mass. So 32.4 grams, because we're told that in the question, divided by 44.01, which should be quite straightforward to calculate, and that's 0.736 moles. Okay. Now, if I've got 1 mole of carbon dioxide, I must have 1 mole of carbon atoms. If I've got 0.736 moles of carbon dioxide, well, I must have 0.736 moles of carbon. Okay. Now, let's find the number of moles of water. Why would I do that? Well, because if I know the number of moles of water, then I know something about the number of moles of hydrogen in my sample. So this again is mass over molar mass, 6.63 over 18.016. Again, that's something you should be able to calculate quite easily. And that equals 0.368 moles. Now that is not the same as the number of moles of hydrogen, because there are two hydrogen atoms in one water molecule. So the number of moles of hydrogen will be twice that, which is 0.736 moles again. Okay, we should easily be able to see that that is a 1-to-1 ratio, and therefore the empirical formula is going to be CH. Okay, now that I've found that out, I should be able to find the molecular formula if I'm told the molar mass of the substance, but I'm not again. So let's see how we're going to do this. I'm just going to get rid of all that text there, I'm just going to come back to the fact that our empirical formula is CH. Okay, and I could find the molar mass, so-called, of my empirical formula. So this isn't a substance, it's just the lowest possible ratio, whole number ratio of atoms in benzene. If it was a molecule, then it would have a molar mass of 1 carbon, which is 12.01, plus a hydrogen, which is 1.01, which equals 13.02. Okay, so that's the molar mass of my empirical formula. What I need to do is to take my real molar mass and divide it by the molar mass of the empirical formula. I haven't been told this, as I've just said. Okay, how can we get around this problem? Well, we're told, look, we're told a mass and a number of moles of my sample. So I know little m and I know little n. Do I know a formula that tells me capital M? Yes, I do, because it's measured in grams per mole. If it's measured in grams per mole, then that's mass being divided by the number of moles. So the molar mass of my substance is actually 10.0 over 0.128. And if I give that answer to 3 significant figures, because all my data's got 3 significant figures, then this means that the molar mass is 76.9. Now, I can put that into here, so that equals 76.9 divided by 13.02, I should say, and not exactly, but that's roughly equal to 6. Okay, so that means that my molecular formula is 6 times bigger than my empirical formula. So my molecular formula must be C6H6. Okay, so there we go. That's basically the end of the solution to that problem. As you can see, there's quite a lot of similarities to the problems that we've already had a look at, but here we're just being asked to work out a few more things. None of them are new, notice. Okay, they all use formulas that we've learned before in the previous films, but if any of this stuff that you're supposed to be able to do by the end of this film, if any of it doesn't make sense or you're not sure about it, please come and ask as soon as you can. Please practice some problems if it does make sense so that you can get better at them and remember them. And if you've got the urge to post a comment on YouTube, then that would also be very much appreciated.